Good morning, one and all. So the paper ID is 132, and the topic on which I'm going to present is on identification of key environmental factors affecting atmospheric corrosion of mild steel using machine learning techniques. So the authors are myself and few of my students, Astos Patra, Sumanta Mahanta, Anvita Anusri, and I belong to the Department of Metallurgical and Materials Engineering Department, Indira Gandhi Institute of Technology, Sarang. So I would like to thank the organizers for giving me an opportunity to speak on this topic on this conference on cutting edge technology in computing, communication, and intelligence, ICCTCCI 2025. So next is the introduction. Why actually this uh, atmospheric corrosion is a problem? As you can see, mild steel, which is a very common grade steel being used in various applications many structural applications, and so the corrosion of this mild steel, it has serious issue affecting infrastructure, transportation, and manufacturing sectors, which leads to economic losses and structural failures. Because, as you know, that mild steel is a important structural material. Whatever infrastructure work is going on, whether you talk about the reinforced concrete or um, uh, uh, the steel bars that are being used in reinforced concrete, and number of other applications involves mild steel, and corrosion of mild steel will always make that particular material vulnerable to failure. So next, challenges with traditional prediction models. So people have used various traditional empirical models, example Weibull generalized power law, but they struggle to account for the complex environmental interaction, because when the steel is exposed to atmospheric environment, you have whole lot of parameters. For example, to take an example like relative humidity in the atmosphere, the chloride content in the atmosphere, the sulfur dioxide content in the atmosphere, and the amount of rainfall and that it is receiving at that particular time, the amount of sunrise that it is receiving, um, uh, and all many other parameters, etc., etc. So the atmospheric corrosion process is a complex phenomenon because it involves whole number of parameters which affects the corrosion behavior of the substrate or the steel that we're talking about, talking here. Okay, so these empirical models, they gave a limited accuracy in as in service condition or real world conditions. So people have used machine learning to predict corrosion. The machine learning techniques like random forest regression and correlation analysis improve the predictive accuracy of the corrosion rate. It can process, the advantage is that it can process large data sets and identify key environmental factors. So the objectives of the study is that to use the machine learning techniques to predict mild steel corrosion under Indian atmospheric conditions, identify critical environmental factors, example humidity, temperature, pollutant levels, as you can see, the chloride and the sulfur dioxide concentration, enhance corrosion monitoring and industrial maintenance strategies. Next is the background of this topic. That's the mild steel corrosion. As I said in the introduction section, that it's a major issue because mild steel being used as a very important structural grade steel. It is when it is exposed to the atmosphere, due to the effect of various environmental parameters like humidity, temperature, pollutant level, it leads to corrosion. I know it gets oxidized, forms oxidized layer on the surface, rusted, and that can lead to mechanical failure also. So the limitation of traditional model, as I said, empirical models people have used, but these are not efficient in predicting the accuracy. So that's why people are using recently machine learning techniques to analyze large data sets that is available, the corrosion data set that is available. Utilizing that, they're predicting the corrosion rate using various machine learning techniques. So the research motivation is that to enhance the predictive accuracy for proactive maintenance and cost effective industrial sustainability. Literature survey, so there are whole there's few papers, few number of few maybe 50, 60 papers that are available, with the use of machine learning and corrosion prediction, particularly atmospheric corrosion. Okay, so here we have I've just included three important papers. Yan et al, this Chinese fellow, they used Pearson correlation and machine learning to identify the key environmental factors, and then after identification of the environmental factors, they go for this random forest and SHAP analysis. These are machine learning algorithms to determine the most influential factor. That means the most influential factor affecting the corrosion behavior. Then again, another one by G et al. Developed a random forest-based model for atmospheric corrosion rate prediction, integrated Spearman correlation to filter out less significant factors. Then Z et al. They analyzed 16 years of corrosion data. You see that 16 years of corrosion data from 17 low alloy steels, a huge database, found that pH and environmental factors, they significantly affect the corrosion over time. So what key findings we get from the literature is that the traditional model, they are ineffective in predicting the corrosion behavior. Then machine learning, especially random forest, enhances predictive accuracy. Feature selection techniques, Pearson or Spearman correlation, they improve the model efficiency. So the problem identification, the issue first is that it is the corrosion of the mild steel which affects infrastructure, transportation, manufacturing, leads to structural degradation, safety risk, and economic losses. And the challenges with the traditional prediction models, these are empirical models. They struggle with complex environmental interactions. They have limited accuracy due to oversimplified assumptions, reactive maintenance that increases downtime, repair costs, and material wastes. So, need for an improved approach, where you can have this thing without any exposure, actually, without carrying out any experiment, but by using the previous data, if you can predict the corrosion behavior, that will be helpful. A data-driven AI-based solution is required for accurate, proactive corrosion prediction. Machine learning can analyze large data sets, detect patterns, and improve maintenance strategies. The methodology that we have employed here in this paper is initial is that you have to first collect the data. It can be collected from the literature or the database that is available. So we have collected data from the literature, mostly the Indian corrosion data. That means the steel, the mild steel which has been exposed to Indian atmospheric conditions. So that data from the literature we have used, and then we have pre-processed the data, that is clean and normalized data, remove redundant parameters using Pearson Spearman correlation. We have used to remove the redundant parameters. Then we have gone for feature selection and ranking to identify the key influencing factors using correlation analysis and random forest regression. Then we have gone for model development, that is train the machine learning models and compare performance with traditional methods. Then prediction and validation, test the model accuracy using validation data sets, optimize performance for better predictive accuracy. Then we have implemented and monitored the model, that is the machine learning model, for real-time corrosion monitoring, support predictive maintenance strategies. Results and discussion. So, as you can say, it's a hybrid model. Initially, it's a Pearson Spearman correlation plus the random forest algorithm we have used, and this is the corrosion data set that we have obtained from the literature. As you can see, it has data from 15 test sites starting from Chandigarh to Kalamassery, and it has a number of parameters like, though it's a small database, but it's a very significant one. Annual temperature in degrees centigrade, the relative humidity in percentage, the rainfall that it has received, then chloride concentration milligram per meter square per day, and sulfur dioxide milligram per meter square per day. Okay, so this is the database for the corrosion of the mild steel samples. So this is, as you can see, that the results and discussion part, both as you can see, the Pearson correlation result as well as Spearman correlation result. The analysis, as you can see, identified minimum relative humidity, maximum and minimum annual temperature, rainfall, chloride, and sulfur dioxide as the key environmental factors influencing the corrosion rate of mild steel. And correlation analysis using this Pearson and Spearman methods, it shows that a strong relationship among these parameters with minimum relative humidity showing the highest correlation with the corrosion rate, as you can see from the figure. This indicates that humidity plays a significant role in accelerating the corrosion, atmospheric corrosion, particularly in environments with fluctuating moisture levels. The application of this random forest regression, okay, as you can see, the results obtained from random forest algorithm further refined these findings by ranking that maximum relative humidity as the most influential factor. You can see that the maximum relative humidity, it has the most highest feature importance, as you can see from the figure, followed by temperature variation, chloride, and rainfall. The hybrid approach combining the random forest and Spearman correlation effectively eliminated redundant parameters, improving the accuracy of prediction and enhancing dataset efficiency. The results demonstrate that, as you can see, that machine learning techniques, they outperform, traditional empirical techniques, offering a more reliable and data-driven approach to forecasting material degradation. As you can see, these findings highlight the potential of artificial intelligence driven corrosion monitoring and predictive maintenance in industrial application. By integrating machine learning with environmental data analysis, industries can implement proactive strategies to mitigate corrosion related damage, optimize maintenance schedules, and reduce economic losses. The study reinforces the effectiveness of automated corrosion prediction models, paving the way for more efficient material longevity in management in infrastructure and manufacturing sectors. So, conclusion, as you can see, the study, what it highlights, it basically highlights the uh, machine learning techniques which enhances the accuracy of mild steel corrosion prediction. As you can see, the key environmental factors that we have identified as humidity, temperature, chloride, and sulfur dioxide, which significantly affects the corrosion rate. And the key findings, traditional models, as we have explaining from the beginning itself, that they struggle with complex environmental interaction. Random forest regression and correlation analysis provide superior predictive accuracy. Future selection techniques improve model efficiency and reliability. Practical impact supports proactive maintenance strategies, reducing material degradation, enables automated corrosion monitoring for industrial application. Future prospects, you can use further database, large database for greater predictive accuracy, integrating real-time AI-driven monitoring systems. So these are my references, and thank you. Just to explain a bit detail about atmospheric corrosion is that when we expose the steel sample to the direct atmosphere, that means it's a field-based corrosion monitoring. Okay, when we expose the steel to the direct atmosphere, whole lot of number of atmospheric parameters like rainfall, like sunlight, like wind speed, like relative humidity, pollution levels, like corrosive chloride content or sulfur dioxide content, they affect the corrosion behavior of that particular steel. So atmospheric corrosion itself is a very complex phenomenon because you have whole lot of parameters that is involved on in this. And these steel samples, they absorb water droplets from the atmosphere, or maybe by the rainfall water falls on the surface and they absorb chlorine uh, or other salts onto that surface, so it forms a thin electrochemical layer on the surface of the steel and proceeds the corrosion. So that is the basic of atmospheric corrosion. So thank you very much, and I once again thank the organizer for providing me the opportunity to speak on this topic. Thank you very much.